first begin with a quick understanding of how comfortable you guys are. Um, so, beta, the equilibrium situations. Chavi, beta, what do you understand about the equilibrium? What do you mean by, or what is meant by equilibrium? And what is your understanding? What kind of questions have you done on equilibrium till date?
So like equilibrium is essentially when all the net force in the entire system is zero.
Okay.
And as for like the kind of question, like I don't know how to tell you what kind, but I think I've done a few, like quite a few.
Quite a few. So let's see what kind of questions we would be dealing with. So let me walk you guys through the first 10 question types on equilibrium. Starting with the first one, here we will look at scenarios wherein we have a particle or we have a rigid body, with particle or rigid body experiencing multiple forces. Now, those forces might be your tension forces, might be gravitational forces, might be electric forces, but not the frictional forces. Okay. So, why we are not including the friction forces here? Because we have saved them for the question type 3 onwards, right? Because dealing with the friction, we have to be careful about few things. So we'll learn about those different things that we should be very careful about when dealing with static friction or for the kinetic friction. So first, the question type once again deals with particle or the rigid body under multiple forces. Okay. So when we are dealing with a particle, we say the sum of the forces in all the three directions should be zero. Right, Peter? Correct, Namita? The sum of all the forces should be zero.
Yes.
Now, if you're dealing with a rigid body, an extended rigid body, say a ladder or an extended rod or a cube or a cubical block, in that case, also make sure that sum of all the torques about the different axes is also zero. Now, are you guys familiar? I know Ruchika, Bita, you have gone through it, and I'm guessing Chavi, you are also quite familiar with torque. Is that right? Or at least you understand what torque is.
So kinda.
Right. So, Bita, torque is the twisting action of the force, right? The twisting action of the force. Um, Example being, if you recall our day-to-day observation, so let's say we have a door. We have the door knob here. If you try and apply a force at this point, you feel that you can easily close the door, right? You're able to close the door. If you apply the same force, let's say near the hinge, will you be able to close the door? Will you be able to rotate it about this axis?
No.
You will find it very hard to do so. Very, very hard to do so. Force is the same, but still the outcome is different. So what has changed in the two scenarios? Different in the two scenarios. What's different is the distance of the point of application of the force from the axis about which the body is rotating. Okay, so in this case, the door cannot move linearly, but rather it is fixed on the hinges and it can only rotate about the hinges, about the axis that are shown by the dotted line. So what we just learned is that besides the force, what is important is the distance of the application of the force from the axis of rotation. So we'll call it distance r. Okay. So r in some ways is similar to the position vector. Position vector, right? So this is the force F. So torque, which is also a vector quantity, is defined as r cross F. R cross F. So when we are dealing with the extended rigid bodies, we have to ensure that the not only all the sum of all the forces is zero, but the sum of all the torques should be zero. So let's see if we can think of a scenario wherein this seems to be important. Right. So let's see if I can draw this cubical body. Let's say if I apply a force of 10 Newton at the top and I apply a 10 Newton at the bottom. Now, in the next sentence, I'll use certain words which will be new for you guys, but don't worry about those. We will learn about those terms in the upcoming classes, upcoming chapters. So if you look at this body, the net force on the acting on the body is zero. But we know from our experiences in our day-to-day lives, just from our intuition, we know that this will rotate about this axis. Correct, na beta? The box will rotate if we apply these two forces. In fact, it will be rotating with angular acceleration, right? With angular speed increasing. The center of the box, and later on you will hear the word center of mass. The center of mass of this body will not be moving, but the body will start to spin faster and faster. So question is the body in the equilibrium? Of course not, right? Now, typically, the torque part is introduced in the later chapters. But for me, I think it's not that difficult a concept that we have to save it till rotation. The other thing is when we get to rotation, you will have influx of many concepts all of a sudden. So being familiar with one concept from this point is not going to hurt. It's going to help us. Okay. So for the first type of question, once again, we'll be dealing with scenarios with a particle or an extended rigid body under multiple forces, multiple external forces, but with the particle in the body being in equilibrium, for which we have to equate all the sum of all the forces along x direction, along y direction, along z direction to be zero. Similarly, torque about the x-axis, torque about the y-axis, torque about the z-axis should be zero. In the second question type, you might be given the potential function, or potential energy function. So what is potential energy? What is that function we are talking about? Again, we'll learn that in the next class. Potential energy is nothing but a simple way of capturing the work done by conservative forces. And why do we do that? And I'm going to repeat the same thing multiple times in the classes ahead. But good thing about conservative forces, like the gravitational forces, the path through which you take a body has no impact on the work done, on the magnitude of the work done by the conservative force. So the work done by the conservative force would remain the same. Work done would remain the same. It only depends on the initial and final points, not on the path followed. So then for the physicist, they realize that if that is the scenario, then why do I have to calculate the work done by, say, spring force, which is also a conservative force, every time I compress a spring? right? Because I know the work done by the spring depends only on the initial and the final condition, not on the path taken, not on how the spring has been compressed, how the body has been taken from the bottom, from the ground floor to the top floor, whether you've taken the lift, whether you've taken the ladder, whether you have flown through a helicopter, doesn't really matter. The work done, if you take something from the ground to the top of the building, will remain the same. So to avoid calculating the work done by such forces every time using the standard definition of the work, which we will study in the next chapter, the potential energy concept was introduced, which is essentially the potential change in potential energy was defined as negative of the work done by the conservative force. Once again, what is potential energy? It is a measure of the work done by the conservative force. Beyond that, we'll worry about that in the next class or in the next chapter. Now, the definition, I'll write it down here. Definition was, once again, potential energy, we always define the change in potential energy, right? The potential, that's how the definition is. The change in the potential energy is work negative of the work done by the conservative force. Okay. F dot dr. This is du. Scalar quantity. F is a vector quantity. The displacement is a vector quantity. So we have a dot product here, which is scalar. So du is F dot dr. Now, if you are given the potential energy function, right? Potential energy function. So question is, can we figure out the force if we are given u? Of course we can. We'll use the same definition and we'll just reverse it a little bit. We'll say du by dr minus du by dr is force F in that direction. Okay. Now, if you have begun to think of the intricacies in going from here to here, you can either ask them now, or I'll not talk about the intricacies at this point in time. This is good enough. Okay. Because the scenarios we're going to be dealing with are relatively simple. Okay. Then in the next question type, number 3, we'll be dealing with scenarios involving static frictional force. Static frictional force. So what does it mean? That the object or there is no relative motion between the two surfaces, right? Between the two surfaces, which would have the tendency to slide against each other, but there is no relative velocity. So there is tendency to move, but there is no actual movement. So let's take an example to understand the nuances better. So let me quickly draw up a table here, and let me just draw some. Okay. Let's say you place a book here. Now, nobody is pushing the book. So if I were to ask you, Chavi, how much is the frictional force? So before I ask you any question, let me give you some data. Let's say the coefficient of friction between the book and the table is, let's say, 0.2. And let's say that the mass of the book is 10 kg. Okay. So in this scenario where the book is placed on the table, there is no horizontal force acting on the book. How much will be the frictional force on it? What will be the frictional force on the book?
So 0.
0. Now, if I were to apply force of 1 Newton, what will be the frictional force?
So 1 Newton.
1. And the direction will be opposite to the applied force. What if we increase it to 2 newtons? assume G to be 10, not really 9.8. That's what I'm not trying. Um, so if you apply 2 newtons, what will be the frictional force?
So still 2 newtons.
Still 2 newtons. If you apply 3 newtons,
So 3 newtons.
assuming that the coefficient of static friction is equals to the coefficient of the kinetic friction. What will be the frictional force, Peter?
So 3 newtons.
Aha. So I made a mistake here. I should have said 1 kg, not 10 kg. Now, I think you got the gist, right? So now in this case, what will it be? It will not exceed 2 newtons if you have mass as 1. Correct,
Yes, sir.
okay. Now, what's your understanding of the frictional force, Peter? What is it really? So let's say I have two surfaces. So what causes the frictional force here? What is the cause of the frictional force between two bodies?
So उनकी surfaces में वो interlocking होती है तो
Sure. Surfaces are not really perfectly smooth, but rather you have riggedy raggedy or zigzag surface, correct? And similarly, you have the same thing for B as well. If you were to look microscopically, that's how it will look. So what happens when if it were all flat, that was 1 kg. So this mass of 1 kg, that means the gravitational pull of 10 newtons is spread over the entire surface. That's how it looks to a naked eye. But when you look very closely using a microscope, what you will see is the contacts are very small, right? Let's say here, and here. And the contact areas are very, very small. So that creates very high stress points at those locations. Okay, so that creates very high stress locations at those points. And that's what causes the interlocking. Okay, and so when you have micro welding going on, right? So there is much heat produced at that point. There is a micro welding going on. The two surfaces fuse with each other, right? At the atomic level, the atoms of A and B start to fuse at the surface. Okay. So now when you try to move it, first of all, you have to break those interlockings. Okay. Number two is, imagine that you are actually trying to pull such surfaces against each other. Right? So you're trying to pull this one to the left, this one to the right. So you will have to break, or some of these you'll have to, because it'll be very difficult to be lifting it up. So you will be shearing, you'll be causing shearing of these tops. And sometimes, of course, there will be gliding going on. So friction is resulting from the interlocking or because of the very small contact areas at the microscopic level. And of course, because of the rickety-raggedy zigzag surfaces. So those crests and troughs, they interlock. And as you try and move, we end up shearing some of this. That's why when you rub something quite a few times, you end up polishing that surface because you are trying to remove, you're ending up removing that roughness or those edges where you're shearing them off as you rub against each other. Okay. So let's go ahead and jump into these and start experiencing or start practicing questions on how to apply the condition of sum of forces should be zero, sum of torque should be zero in question type number 1. So let's begin. Any questions while we are transitioning? No questions. Now, so I do see a question with a Rito Brato. I think you are asking a question regarding the force. What is force? What is motion? I've got 99.9 percentile. So, beta, first of all, congratulations. God bless you. May you have a wonderful exam ahead of you for JEE Advanced. And if you want to be more specific about your question, please do let me know. Okay, so let me go back into the live class. So let's begin, Peter. Now, you guys are comfortable, especially Beta Chavi, you are quite comfortable with the tension forces, the spring force, how it acts, the normal force, the gravitational force. Are you comfortable with all these forces? How do they work? What are the rules of the game?
I think so.
Okay. All right. So let's start with this problem itself. So here we have string with the one end of the string being fixed to the some fixed surface, let's say the roof of whatever the surface that is, and then on the other end you have the mass m. The gravitational pull is acting downwards. So G is acting downwards. If you apply a frictional force F, there, then question is beta, if the applied force is horizontal, then the question is, will the tension in this string and in this string, will they be the same? So let me call it tension T1 and tension T2. Let's say it makes an angle theta here. The question is, if the applied force F is horizontal, then is T1 equals to T2?
No, sir.
No, it's not equal. Okay. And can you imagine a scenario how you can actually do that? Now, you must have learned that the tension in the rope is in a continuous rope. The tension cannot change drastically. So can you tell me what's going on here, beta? Ruchika, beta, can you comment on that? So why will tension T1 not be equal to T2? And under what circumstances can we achieve this kind of a setup?
Sir, if there was a pulley instead of actually the point there, if there was a pulley, then T1 would be equal to T2. But so in this case, sir, the force required to help hold it there will be
so let's say you have a, okay, let's talk about the pulley for a moment, Peter. So for the pulley, to hold the pulley in position, what will be the direction of the net force on the pulley? So let's say the pulley is hinged at a certain wall or certain rod or whatever, right? So it's hinged at the center. Now, what will be the direction of the reaction force from at the hinge? What will be the net direction? Can it be horizontal? Can that be horizontal? So in other words, so let me first explain it. So what I'm saying is, you have the pulley and the string is, let's say the pulley is frictionless, the string is massless, and you have the string wrapped around the pulley. So my question is, if the pulley is hinged at the center, then the reaction forces, right? The reaction forces acting on the hinge due to the support on which that pulley is has been mounted. So you can call them the reaction force or the mounting forces. Can they be horizontal? Let me show them with a different color here. Can they be in this direction? Can they be like this? Would they have to be in this direction, somewhere in that direction?
So I guess the second one.
Second one. Okay. So how come, so can you tell me how we can achieve this kind of a scenario, this one right here, where the tension is not the same in the two part of the string? So what might be causing it? Or how can you achieve that scenario? One way to achieve that is, you take a rope, tie another rope around it, and really tighten it up, right? So that the threads down below and threads up below or up above, they are not they are not they're not feeling the continuity of the tension forces. Now if you were to pull it using a string, right, then you can achieve a scenario wherein you are pulling in the horizontal direction. But when you tie a noose around this point, then you are disconnecting the tension forces. You're causing a break in the tension forces in the string. So, Beta, did that make sense? So, for in such a scenario, you can have, in fact, you need to have, because the answer that you gave was based on your simple calculation of sum of forces in the horizontal and vertical direction, right? So you figured out that, hey, if the tension is the same, then I cannot balance the forces in the vertical direction, right, Beta? Because in the vertical direction, you have T1 cos theta is equals to T2 is equals to mg. So this alone means T1 cannot be equals to T2. Sounds like you guys are pretty clear. So once again, to balance the forces, make sure that you balance them. So go back to the Newton's second law, which is F is equals to ma. It's a vector equation. So the three components are, scalar equations are fx equals to max, fy is equals to my, and fz is equal to az. Now, if the acceleration is zero, saying if the body is in equilibrium, that means the right-hand side is zero, which means, by the way, this should be the net force. Whenever I write the Newton's second law, it's always the net force on the particle is equals to mass times acceleration, right? Not just one individual force, but the net force, the vector sum of all the forces acting on the particle should be equals to mass times acceleration. So which means that the sum of all the forces along x, y, and z should be zero. Okay. And then for the extended rigid bodies, we'll worry about the torques when we come to that. So let's solve a few problems. Okay, let's start with a the students on YouTube, just for your information, um, the way we are approaching these different topics is we are approaching all the different chapters by through the lens. So, what are question types? Question types are different kind of applications for a given concept, right? So, for example, equilibrium, in theory, it is a fairly simple, straightforward concept. But when you look at different types of applications, so as we have divided it up, so there are 10 different applications
So X3R.
on the equilibrium. So anyway, let me go back to the live class, back to the discussion later. How much is it, beta? X is 3.
Yes.
Okay.
So 3
Yeah, okay. Let me read through the question with you guys. It says a meter scale is balanced on a, so let me provide it. This is 1 meter long, is balanced on a knife edge at its center. When 2 coins each of mass 10 grams are put one on the top of the other at the 10 centimeter mark, so let's say uh, from let's say it's starting from here 1 till 100 centimeters at the 10 centimeter mark, so let's say right here, starting from 0 to 10 centimeters. So if we put the 2 points, it's 20 grams. The scale is found to be balanced at 40 centimeter mark. That means the scale has to be now put on. Initially it was at 50 centimeter mark, but now it has to be at 40 centimeter. The mass of the meter scale is found to be this. The value of X is how much? So here we have to use the concept of the torque. The sum of all the torques about the balance point, about the point where we have balanced the meter scale on the knife edge, at that point, we have to find the torque due to all these forces at the meter scale and then balance them out. The torque should be 0. Net torque should be 0. Definition of torque due to a force F about the point of interest or about the axis of interest is given by R cross F, R being the position vector from that origin or from that axis.
Sir, इसमें एक doubt था.
Yes, बेटा.
सर तो मास ऑफ द होल मीटर स्केल अगर हम निकालेंगे तो सर हमें लेफ्ट साइड जो पोर्शन है उसका भी तो मास लेना पड़ेगा.
can go to the concept of center of gravity, which says that the gravitational force acts at the center of mass.
Oh, so the right side का weight होगा वही left side का भी weight होगा basically.
So we can actually kind of take the whole mass to be on the right side at a distance of 50 centimeters.
So for the, let me use different colors here. So beta, as far as the gravitation force is concerned, so net gravitational force acting on a body, on an extended rigid body. This is an extended rigid body, no? So the gravitational force is acting on every atom, every molecule, right? But you can replace all those, you can sum up all those forces and put an equivalent force at the center of mass, which means we can have the equivalent force here. This is mg acting here. Mg is nothing but this x into 10 to the power minus 2 times g. Gravitational force acting on the scale. Now you have 40 grams here, so there is this force acting here. This is 40 grams. 40 grams into 10 to the power minus 3 into g. And you have to balance it about this point. This point is how far? This is 30 centimeters. And how much is this? 10 centimeters. So what is the torque due to this mg? About the point O, about this point, R, this is R cross F. Both are perpendicular to each other, so R cross F will be RF sine 90 or RF, which means 10 into mg. What is the direction of this torque? Well, the direction is pointed inwards into the screen, Now, if you look at the force on the left, the torque due to this will be R, which is 30 centimeters, into F, 40 into 10 to the power minus 3 G. Okay, and this is pointed straight out of the screen. This is pointed perpendicular to the screen coming out. Okay, so the two the two torques should be equal in magnitude, right? If I were to draw it in three-dimensional view of the same thing, so one torque is acting this way, torque is acting this way. Both the torques should be equal. No, torque is a vector quantity. The direction is given by the cross product rule, right? You guys, Chavi, table no beta? If this is vector A, this is vector B, then A cross B would be this vector. And how you do that is along A with the keep your hand along the with your the palm face towards the B vector, and then rotate the fingers from A to B. The direction of the thumb gives you the direction of this vector A cross B. A cross A would be in this direction. And always rotate about the smaller angle, right? Rotate about this angle if you're going A cross B. If you're going B cross A, rotate like this. Ruchika beta?
Yes, sir.
Okay. So 12 into 10 to the power minus 2 kgs.
Sir, so the alternate method, can it be that we take the whole mass to be y for the meter scale, and then we can find out mass per length, so we can do y by 10, 100 centimeters, and then we can see, but sir, we don't know exactly how much is still left. Yes, sir.
I understand what you're trying to do. You're trying to say, if you take the weights, the 20 gram points, plus the scale as one system, can you figure out its center of mass? That should be on top of the point O. Otherwise, it will tip over, right? It cannot have equilibrium.
Yes, sir.
That may be slightly more complicated than this. A quicker method. You're more than welcome to. It's one of the same thing. Remember, m1 x1 plus m2 x2 is equals to m1 plus m2 xcm. If you say xcm is at O, this is 0. X2 is mg. And this one is minus 40 into 10 to the power minus into g into 30. This is equals to 0. Again, the same equation. No?
Sir,
Yes, Peter?
इसमें हमने इसको 10 mgc क्यों equate किया?
Oh, R cross F. So we are equating the torques, twisting action of the force about the, because one force, this M rotated like this, the other one is trying to rotate it like this. The twisting action of the two forces should be equal and opposite in direction. So the net twisting action should be 0 if it is to be in equilibrium about that knife, about the point O. So once again, let's say this is just a meter scale. So if you put your knife here, this is going to tip over, no? Correct number?
Yes, sir. Huh.
Now, if you put enough weight in here, you can still hold the balance here. So what does that mean? The twisting action, because there was a gravitational pull here, which was generating the twisting action. It was trying to twist it about or rotate it about this point O. It was trying to rotate it like this. Now you have enough mass on the left hand side to counter. So the left hand mass is going to counter with this twisting action such that the net twisting action is 0. Sum of all the torques should be 0, where torque due to individual forces given by R cross F. So torque due to the first force, R1 cross F1, torque due to the second is equals to R2 cross F2. And we have to find a vector sum of all these torques. Okay? And equate that to 0. On the scale of 1 to 5, what is the comfort level here? Beta, what is the comfort level?
So 4.5.
4.5. Chavi beta, what is the comfort level?
So like maybe 4.
That's pretty good. So let's actually look at some more problems and hopefully you will get a hang of it. Perimeter. And just as a quick reminder, concurrent forces, everybody understand what concurrent forces are? So these are when all the forces, their lines of action of all these forces pass through the same point, then the forces are concurrent.
So both are true.
Okay.
Yes, sir, both are true.
So I'll read through the question. Consider a frame that is made up of two thin massless rods, AB and AC, as shown in the figure. A vertical force P of magnitude 100 newtons is applied at point A of the frame. Suppose the force P is resolved to arms AB and AC of the frame. The magnitude of the resolved component along the arm AC is how many newtons? And they have given the values of sine 35, cos 35, and sine 110 and cos 110. Yes, madam. You may be overthinking the question because we are so afraid of such questions because the question might ask you about the reaction forces and you will have to do the force balance, you'll have to do the torque balance because the images you have in your mind is ladders leaning against each other, ladders again leaning against the wall. But just check again, what is the question asking?
So 81.9 newtons.
81.9 newtons, yes?
Yes, sir.
And nothing wrong in double checking just to make sure whether it is can be really that straightforward. Yes, of course. Sometimes they also test it, no? They see if they can throw the students off their balance.
So, but there is a question in the, I guess, some other question like force and motion only, where sir, we were asked to find out the reaction force, I guess, or the tension in arms A and B. I'm not sure.
Right, right. Such questions will be there as well. Okay, we'll come to this. Chavi Beta, are you clear? They're simply asking the component of the force P along AC, so that cos of 35.
Yes, sir.
Yeah, okay. Let's. While the students in the class are solving these problems. So I hope you guys listen to this lecture later on. What's important is to practice the questions on a regular basis and practice them smartly, right? Understand the different scenarios you are trying to solve. So we have divided this chapter into about 39 different types of questions. So if you develop, or 32 different types of questions. So if you develop the a skill to solve each one of them, then you are in a very good position to solve any question that is thrown your way, right? Whether it is maths question or IUQP question or JEE mains question, and of course, NEET questions are fairly simple and straightforward. Any exam, any other exam, whether it's BITS or the MHC or Velour or whatnot, you should be able to solve those questions very easily. So from the get-go, from the beginning, start building this ability to solve all these different types of questions. There is not much of a point in solving 10 questions, 20 questions of the same type and miss out on the other question type. You should not do that. Make sure that you get a good coverage. This approach will definitely help you get a much understanding of the concepts, right? So in any case, so let me get back into the class. Yes, Peter? So can I provide some thinking points? So Peter, uh, you can write one equation, force balance equation in the vertical direction, right? So tension T1 plus T2 must be equals to 3 mg. Okay, so that is your first equation. How many unknowns are there? There are two unknowns, T1 and T2. So you have to make use of the other equation, which is not the force balance equation, because you don't have any forces in the horizontal. So you cannot really write any other new equation in the horizontal direction or in the direction perpendicular to the screen, right? So there are no forces in those directions. So we still need one more equation, and that will be the torque equation, the balance of the torque. All the torques about about what point? You can take any point you like. And that is something that I do wanna. Can I grab your attention, beta Chavi?
Sir, is it coming out to be 1 mg?
1 mg? Okay. So let me quickly do that in my head. So 2 mg times 25 plus the plus mg into 50. So that is again 4 mg into 25. That is 100 mg, 100 centimeter into mg is equals to 100 into tension T. So that is 1 mg. Yes, looks like it's correct. But so Ruchika beta, can I ask you a question?
Yes, sir.
So in this one, when you wrote the torque balance equation, right? So around what point did you write it?
Sir, about B.
About B. Why? Because that was the most convenient to figure out the tension. When you write your torque about the B should be 0, you will need to figure out the tension in this one.
Yes, sir.
Right? But here's the question for you, Peter. So we wrote first equation was TA plus TB is equals to 3 mg. Then you had to write another equation, which was sum of all the torques about a point P in the Z direction. That means in this direction, perpendicular to the screen. That should be 0. Now, what should be the point be? You chose here, somebody can choose in the middle, somebody can choose it here, somebody can choose here, right? So you can, or you can in fact write your torque balance about this point as well, about this point. You can write it about this point on the screen. You can do all sorts of crazy stuff. Now, which point you pick it according to your convenience. But the question is this, right? If this is true, then I should be able to write infinite number of equations for my unknowns are only two. So what does that mean then? I can write so many equations. Unknowns are only two.
So but all those equations are interlinked.
Yes, they are all dependent equations. What does that mean? If I write the equation about torque about the z direction equals to 0, this gives me an equation, right? I can write about, let's say this is point C, this is point D. I can do the same thing about C. I can write the same thing about D, but using this equation and using, let's say you wrote this one. From these two equations, you can derive this one, you can derive this one, you can derive any other equation, right? That's why we only have two independent equations. Rest, all the equations are dependent equations. So that takes off one worry, right? When you are trying to write torque in the, what is the z direction? Let's say this is x direction, this is y direction. So z direction is pointed out of the screen towards you. Okay, so now when you're writing torque about the z-axis equals to 0, but which point, axis point, doesn't really matter. You can take any convenient one, but you only get one equation. Right? So why is that important? Sometimes you get a problem like the two-letter problem. That's the one that's coming to my mind right away. Sometimes you say, okay, I can write a torque balance about this one. I can write a torque balance about this one. Write a torque balance. Wow, I'm getting so many questions. There are not that many unknowns. Solve them. I do not get take that. They're all dependent equations. Only one independent equation for torque balance in the z direction. There will be one independent in the x direction. If there were any forces to result, which will result the torque in the x direction, which are right in this scenario. Correct, Namita?
Yes.
Okay. Did this make sense, what I just said?
Yes, sir.
On the scale of 1 to 5, beta, just quickly. Scale of 1 to 5.
So what you just said makes sense, but can you help me with the talk part of this question? I did not get how to do that.
With the tension? In this case, okay, let's write the torque about B. So let's find the torque B. In the z direction. So this mg acting downwards, mg acting down, this tension acting upwards. I'm talking about torque, net torque on this rod. Okay. So about the point B, about this point, this 2mg is trying to twist it like this with the torque vector coming out of the screen. This is also causing the mg is also trying to rotate it like this. The TA1 is trying to rotate it like this. The net sum of the twisting actions should be 0, right? Which means the torque due to 2mg force about point B plus torque due to mg force about point B plus the torque about torque due to TA about point B, the sum of the three should be 0. Okay, so if you assume that this is my x, this is my y, and z is pointed out of the screen, then torque due to this is r cross f. What is r? R is this distance. Correct, beta? R is this distance. F is acting downwards. right, beta?
Yes, sir.
Okay. Now you might say, oh, sir, actually the mg is acting right here. It should be this one. This should be r. This is mg. This will still give you the same thing. Why? R cross mg will be r mg sine theta. Which angle? This same. Okay, which is same as this same. So when you write this r mg sine theta, this r sine theta is what, this distance? This is r sine theta, so this is 25. So this will be 25 centimeters into 2 mg. Sorry, this is 2 mg. What about the torque due to this? This will be 50 centimeters into mg. Again, the torque vector is pointed out of the screen. What about the torque due to the tension TA? It is trying to rotate it in the clockwise direction, which means that the torque vector, if you curl your fingers in the direction of the twisting action, your thumb should point in the direction of the torque vector. So the thumb will be pointed inwards, which is opposite, so minus z direction, opposite to the torque due to 2 mg and mg. So we'll write this as minus TA. This will be minus TA into 100 centimeters. The sum of the three should be 0. So what this gives us then is, this is 50, this is 50, so 100 mg, 100 centimeters into mg is equals to TA into 100 centimeters. So TA is 1 mg. Yes, beta?
Yes, sir. Okay.
If you had to find TB, the tension in the other string, then you would take the torques about 0.8. Let's do one more question, then we'll stop. We have not reached our target, but I just want to make sure that we have enough practice under our belt so that we start to feel comfortable. That's why I'm trying not to rush. Let me read this one so that it doesn't seem that scary. A uniform cylinder of mass m and radius r is to be pulled over a step of height a, where a is less than r, by applying a force F at its center O perpendicular to the plane through the axis of the cylinder on the edge of the step. The minimum value of F required is how much? If the language is slightly confusing, then this force is perpendicular to, let's call it A. Force is perpendicular to OA. minimum value of F required.
Could you just scroll down? So I'm not sure, but I think it should be D.
D for Delhi or B for Bombay?
D for Delhi.
D for Delhi. Shall we discuss the question? And this is the last question, after which we'll stop the class.
Yes, sir.
Um, First of all, they're asking for the minimum value of F required. Okay. Um, when is it toughest to lift the cylinder above the edge E? Well, let's look at the torque which is trying to keep it on the ground. That is the torque due to mg. Right? So the torque is actually, I said mg r sine theta. In other words, mg times this distance, right? Because mgr sine theta, as I wrote down, is mg cos theta, mgr cos theta. So this mg times this distance. We will, as we go forward, you will see that we will call it the moment arm of the force. That means the shortest distance from the point about which we're trying to calculate the torque. The shortest distance from that point to the force is called R perpendicular. The torque is force times R perpendicular. That's simple. Okay. Which is the simple outcome of mg times the r times sine theta. So r sine theta will give you this. Okay. Now we have mgr. As you lift it up, let's say you get the cylinder in this position. Now mg is still acting at the center, but now the moment arm, which is the shortest distance to the line of application of the force, which is this one, the r perpendicular is reducing. So the torque applied by mg to keep it down is reducing as you lift it up. In other words, it becomes easier and easier to lift it up as you pull it up. Okay, so it's the hardest point is at when the cylinder is on the ground. That's when you have the maximum torque due to mg about point A. After that, the torque due to mg is reducing because of the shortening of the moment arm, because of the distance between the center of the cylinder and the mg, the line of action of the force mg, and the edge is reducing. I hope that makes sense. If not, I'll repeat it. Now, they are saying what is the minimum value of force F? Well, you can always apply 1000 newtons and pick it up. They're saying what is the minimum required to pull it up? Well, you require the greatest amount of force at the initial point, trying to lift it from this position. So that's why I assume that this force F is providing enough torque to just counter the torque due to mg. That's what we wrote here, and that's what I equated them to 0. So if the force is even slightly greater than this, you will be able to lift it up. Okay, so that's the minimum force. Anything less than this force, you will not be able to lift it. Anything more than this is an overkill. Yes, madam? Chavi, did that make sense? No, I guess not, right?
Sir, last one part nahi samajha.
Okay. Is this part clear that we are just saying it should provide enough torque, just enough torque to counter the maximum torque due to mg.
Yes, sir.
Torque due to mg is changing as you are lifting the cylinder up. The torque due to mg is reducing. In other words, it becomes easier to further pull it up. So you want enough torque to counter the initial torque due to mg. So that's what we wrote here. So the torque due to mg about A is mgr sine 90 cos theta, and the torque due to force F is R. Yes. So we said let's find out how much force is needed to just counter the torque. So that came out to be this mg cos theta, or mg times 1 plus r minus a by r squared. Anything more than this force is an overkill. Anything less than this, you will not have enough torque to counter the mg, gravitational pull, and hence the cylinder will not lift up. Okay?
Yes, sir.
Okay, beta. So I'll stop here and we'll resume on Monday. Right? So we'll resume on Monday from this point onwards. Now I'm going to circulate the JEE advanced practice questions on this topic, and both a note for you and Ruchika. They are really, really good questions. Okay, so make sure that you work through them and work through them with patience. And this is definitely going to hone up our skills. So with that, I'll see you guys tomorrow. Have a good evening.
Sir,
Yes, beta.
sir, एक question था जो मेरे से solve नहीं हुआ था.
Can you please share the question?
Yes, sir.
So for the students listening on YouTube, I'm gonna stop the streaming now, and I'm gonna take on the question.
So the question looks fairly easy, but I'm